For a few days, we're going to be talking about this section over exponential growth and decay. And it's just really a way to apply some of the things that we've been doing. We're also going to, in this lesson, be talking about how to apply it, not just in science kind of relationship, but also we'll be looking at formulas like in banking and things like that to apply what we've been doing. So for exponential growth and decay, again, some of this information I'll read through quickly and some you need to kind of read through on your own. So one thing I want to highlight is exponential functions can model something in growth or decay of some type of initial amount. Now, the basic exponential function we know is y equals a times b to the x power. So what we want to remember here is that a is going to represent your initial amount. B is going to represent your growth or decay factor, depending on what's happening. So the growth factor is going to equal 100% plus the percent rate, and the decay factor is equal to 100% minus the percent rate. So that's kind of the difference. X is going to represent the number of times that the growth or decay factor is applied, and Y, of course, represents your answer. Okay, so here we have a couple of summaries for each type, whether it's something that's growing exponentially or decaying exponentially. So it just again explains what each variable in the equation would represent, and again reviews what that graph would look like, whether it's growth or decay. So you can kind of see the difference in the graphs and also see the difference with whether it's a growth factor or a decay factor. So we're just going to do some examples that kind of initiate this point, or I should say illustrate this point. In this first problem, it tells us a gym currently has 2,000 members. It expects to grow 12% per year. So how many members should it have in 6 years if it has that potential growth? Well, think of our starting point. Our initial value is 2,000 members. So that would be our A value. The growth per year is 12%, so let's change that to a decimal and add the 1. So we would end up with 1.12 for our growth factor. The desired time period is going to be over 6 years, so that will be what x equals, is 6. And so then we would have our function where when x is 6, so we would have, that should be equals, by the way. So it would be y equals 2,000 times our growth factor to the 6th power, which would equal 3,948, which is how many members the gym would expect to have after that 6-year period. So there's an example of how to set it up and how to plug those values into the formula. So let's try one together. We have here, we're modeling exponential growth again. So we have something about cell phones. It states that in 1985, so a while ago, I was in elementary school. Yes, in 1985. There were 285 cell phone subscribers in a random small town somewhere. So that would be our initial amount in this particular problem. That's what we're starting with. So that is our A. It says that the number of subscribers increased 75% each year after 1985. So that will be our growth factor. So we're going to take 1 plus, we're going to change that to a decimal, our percent. So our growth factor will be 1.75. And then it says write an expression to represent the equivalent monthly cell phone subscription increase. If we wanted to know how many in 1994 would have been cell phone subscribers. So from 1985 to 1994, that represents a 9-year difference. So that is going to be our X, a 9-year difference. And then at that point, we're just plugging it into the formula. So we would have Y equals 285, which is A, times our growth factor, 1.75, and then that would be to the 9th power, which represents how many years passed. So we would get approximately, when you plug that all in your calculator, 43,872 subscribers. All right. Again, that's just an example to show that exponential growth. Another type of exponential growth uses what we call the compound interest formula. So it's pretty similar to this formula, except we have a little bit of difference here with the annual interest rate divided by the number of compounding periods. So in this problem, it says, suppose that when your friend was born, your friend's parents deposited $2,000 in an account that paid 4.5% interest compounded monthly. That's important. Sometimes you can use bank accounts that would be compounded yearly. Compounded annually is usually what they say for yearly. Compounded every 6 months. Compounded quarterly, so that would be 4 times a year. So compounded monthly is awesome because that's 12 months out of the year. So that works great. So if we use this formula, pretty similar to the one we just used, again, P is our initial deposit. Our principal is what we call it in what they call it in banking. So we would have, I would plug in $2,000 there because that was our initial amount. And then in parentheses, we have the 1 because it's 100% plus the rate. Well, the rate is 0.045 because it says 4.5%, so we change it to a decimal, and it's compounded monthly. So N represents the number of compounding periods per year. In this case, it would be 12 because they compounds every month. And then N again is here multiplied by the time that passes. So we would put 12 again here times, in this case, 18 years has passed. Because they want to know what will the account balance be after 18 years. So we have our equation set up. I've plugged in my values given, and now we simply need to work that out. It is better if you work it out in pieces versus trying to type all of that in at once on your calculator. So I would suggest you do inside the parentheses first. Gotta get my calculator here. So I would do 0.045 divided by 12. And then, of course, I would add 1 to that. And I would just go ahead, I'm going to put that down there. 1.00375. Then I know that is going to be to the 216th power because I multiplied those. So now I can plug the rest in on my calculator. So I will do 2,000, and then in parentheses, I will have 1.00375 raised to the 216th power. So I can type that all in at once, and I get approximately $4,489.01. So that means after 18 years, the balance in that account would have more than doubled. So imagine if they would have put in more money into that account initially. Really would grow quickly. So that's what we end up with. Remember, when you're doing that compound interest formula for, again, this would be a type of exponential growth, make sure that you work out what's in the parentheses first. Don't try to do all of that on your calculator at once because it doesn't work out very well, okay? Now we have one more example, and this example is just modeling decay. So the first two were growth, and now we're going to look at an example that decays. So in this problem, again, it's a science connection, of course. We have the kilopascal, which is a unit for atmospheric pressure. The atmospheric pressure at sea level is about 101 kilopascals. For every 1,000 increase in altitude, the pressure decreases about 11.5%. So there is our clue that it's going to be decay rather than growth. So that pressure decreases. So what is the pressure if you're at an altitude of 5,000 meters? I'm going to save a little bit of time in the video here. I'm going to stop and write the equation out, and then I'll come back in a second, and poof, the equation will be there and we can finish it up. So just a second. Let me do that. All right, I'm back, and voila, there's the equation. So remember that A represents your initial amount, which in this case is 101 kilopascals. B represents your decay, so you're going to subtract the percent. So we would end up with 0.885 for our decay factor. And then remember, we want to know what's the pressure at an altitude of 5,000. And for every 1,000 increase in altitude, so I divided the 5,000 by 1,000, that gives me 5. So X would be 5. And then you simply take that equation now and plug it into your calculator. So I did have to round. I went ahead and rounded it to 55 kilopascals. So that would be our pressure if we were at an altitude of 5,000 meters. Again, just to show an example of that exponential decay. And we'll spend a few days on this topic, so we'll get a chance to see the growth and decay used in different situations. So we'll spend a few days on this portion. But we'll get to that next week also. And that is the end of our lesson for today. So your job is to now do the assignment, and that assignment is on my website. So have a good day. See you later.